So today we're talking about solid waste management. We've talked a lot about water and wastewater, and in the groundwater remediation lecture talked more about contamination of groundwater and the soil. And now we've got basically two topics left, solid waste and air quality. And we're only going to spend one day on each, and I'll talk about why in a little bit. But when we talk about solid waste, we're talking about waste arising from human or animal activity that's discarded as useless or unwanted. Owners and society believe they have no value. And as we'll talk in this lecture, that's obviously changing as we're starting to try to recover energy and nutrients from our waste, but for the time being, we can think about it as trash or garbage. On the right-hand side here, you can see a diagram from 2010 U.S. What our waste is made up of. You can imagine an army of graduate students sorting through a bunch of trash, trying to categorize what everything was and weighing it to figure out by mass what percent are in these different categories. You can see the bulk of the trash, about half of it, is yard trimmings plus paper, cardboard, and glass, and then the biggest categories being paper and cardboard, plastics, and food scraps and yard trimmings. So what are some of the consequences of improper disposal and reuse? Well, disease. So if you think about food waste, diapers, medical waste, pet waste, pathogens can really thrive in those things. And the combination of that and vectors, which is a fancy word for things like rats, seagulls, flies that would visit the trash or the waste, pick up those pathogens or diseases, and then move to a different place where they can then transmit that disease there. So flies is a good example. Flies can land on like human waste, get it on them, and then land on your food later. That's a vector. So between those two, human health is a big concern. Air and water pollution, so impact on the wildlife, aesthetics, our enjoyment of the water or the air, and then again, human health is another one. Bacteria, viruses, or worms, these are all sort of in the category of diseases, but they can also affect things like agriculture or whatever. And then odors is another one. So we want to be able to properly manage our waste, and we come up with this, they call it solid waste management hierarchy of how would we prefer to manage the waste? What's our preferred order of things we can do? Well, the first is source reduction. If we can just generate less waste, that's the best, because we are preventing the energy from having been expended and the nutrients and the resources from having been expended to make the waste in the first place, like make the plastic packaging or whatnot. But then also we don't have to expend energy or decision making or anything else to process the waste. So that's the ideal. Beyond that, then recycling, reusing, or composting, ways we can get a net increase, or I should say, we get at least partial recovery of the energy and the resources, the materials that are in the product. So this one, if you look at this figure up here, you can see yard trimmings, food scraps, wood, and to some extent textiles, rubber, and leather. These are all actually compostable items, believe it or not. And definitely yard trimmings and food scraps are. And then over on the right-hand side, you can see paper and cardboard, glass, metals, and plastics. We know these are all recyclable. So on this actual diagram right here, almost everything is either recyclable or compostable. This other category represents certain kinds of resins and synthetic materials that may not actually fully be compostable. But if you look around the room you're in, or if you think about your life, almost everything in your life kind of fits in one of these categories. These are the main materials that we use. And then if we can't recycle, reuse, or compost, incineration So especially in waste to energy plants where the heat that's generated from burning the trash or the waste can get captured and converted into electricity. At least then we're recovering some of the energy, even if we're not recovering much of the resource. Landfill with methane capture and electricity generation, again similar to incineration or waste energy, where some of the energy, the carbon-containing material in the waste is getting converted to methane, the methane harvested and then burned and converted into electricity. If not that, then a plain old landfill where at least we can protect the waste from contaminating the environment, from getting people sick. That would be an option. And then the last option would be like backyard burning, right? So like I just burn my trash outside. I don't, but if I did that, at least I could keep some of the bacteria, vectors, disease, things from happening, but I'm not recovering any of the energy or resources, and I'm potentially polluting the air or releasing greenhouse gases, for example, that could contribute to environmental problems. Okay, so again, there's a hierarchy in that we want to do the things at the top, we don't want to do the things at the bottom, and there's an order involved to those. And I'll mention this again at the end of the video, but I've posted 4 different videos on Foxtail that go into these in a little bit more detail than I'm going to in this lecture, so you can watch those videos and learn about these techniques. If you look at the whole process of what we do with waste, from generation to storage like when I generate my waste, I throw it in the garbage can in my room. It's being stored there for a while before I empty that trash can into a bigger trash can or a dumpster, where then it's being stored for a while longer. It's then collected or transported somewhere where in like city of Newburgh, a lot of it's taken to the transfer station, some of it's taken directly to a landfill, or it's taken first to a recovery facility that's not the transfer station, then to the landfill. So different techniques, but a lot of the engineering comes into play over on the right hand side here. The left hand side is a lot of what the actual garbage companies deal with, and people who drive garbage trucks or people who collect the waste one way or the other. And then on the right hand side, engineers come in saying, like, how do we design a composting facility or an incinerator or a landfill, that sort of thing. Okay, so what is a landfill? Landfills are one of the primary ways that we process our waste and manage our waste in the U.S. It's a long-term containment facility, and the idea here is we want to be able to store the waste in the smallest practical volume, usually for a very long period of time, so that it can break down in a managed, safe environment. And modern landfills are, they're not just heaps of garbage. They're technically advanced and have many environmental protection systems. So you can see this diagram from your book where you've got the municipal solid waste in here. You have usually a liner. So it says compacted clay and geomembrane liner to keep infiltration from getting all the way through into the soil. So water rains on the waste, picks up a lot of pollutants, and then can't make it down into like the groundwater below. And if it does make it in, there's maybe a leachate collection sump where it can drain to. Perforated pipes down here that can drain to that sump, and that can be pumped out into actually to a wastewater treatment facility. You've got wells, lots of monitoring wells, monitoring both the groundwater as well as vapors that could be coming out of the subsurface. You've got cover over the top at the end. There's different techniques here. There's dry tombing, where you're trying to put a low permeability cover, like even another geomembrane over top, so that no water can infiltrate down into the waste, or at least very little. Then that waste is staying dry. There's also other techniques where you're allowing some water to infiltrate to try to enhance some of the degradation. Different techniques, but either way, we're trying to limit the amount of water that comes through, at least control it. And then if you have runoff from the top, you've maybe got retention ponds on the side, other kind of berms that would direct surface water to a wastewater treatment facility. I didn't mention here on the top right a little table that just shows how much municipal solid waste has been generated in the United States over time. So you can see generation 1960, 0.44 megagrams per person per year. And 1970 it goes up, more consumption, more waste per person, 80 higher, 90 higher, 2000 higher. And then you can see in 2010 it's actually decreased a little bit. And to 2020, it's actually decreased a little bit more still. People are starting to, both companies in their packaging as well as people in their decision making are trying to generate less waste, which is a good thing. Recycling, you can see, has gone up quite a bit from 0.03 megagrams per person per year to 0.19 in 2010. Composting used to not really happen. Now there is a significant amount of composting happening, especially regionally in certain areas. Incineration went up a lot in around 1990 and then has stayed mostly stable. Incineration is very common in Europe and also parts of Asia, but not very common in the United States, at least not yet. Incineration is very useful where landfills are not used as much. You can see landfills have been quite prevalent. In the U.S., we have a lot of land space, and so landfills are easier and cheaper alternative than incineration. In Europe, where there's not as much space, not as much land, unused land, incineration is more common. This is a little diagram showing the landfill. You've got like daily amounts that are contributed, called daily cells. This is the waste that's being dumped. And then every day there's daily cover that covers that, so that seagulls and vectors and odors and things like that can't get to it. So that daily cover could be like construction cut from construction sites, or it could be biosolids from from a wastewater treatment facility. It could just be raw soil that's dug out or was dug out from the landfill originally when it was built. Anything to just cover that waste up. And again, a lot of the engineering goes into how do you minimize the size of these daily cells? How do you logistically start filling in a way that makes sense? How do you get trucks access to places? How do you design those cells in terms of volume and shape and size? How big does the whole landfill have to be for your service area, for the expected lifespan of the landfill? That sort of thing is a lot of what the engineering behind these goes into. And I'm not going to go through I'm not going to make you do a lot of problems associated with these. Your book talks about those techniques, but I've found that unless you become a specialist in that area, it's unlikely that most engineers will do those kinds of calculations. They're fairly straightforward calculations, mostly volume calculation, some geometry, that sort of thing. But okay, I thought these figures were interesting too. You can see through the life of a landfill what kinds of gases get produced. So a lot of nitrogen and oxygen initially, this big peak of carbon dioxide followed by a leveling off. Methane coming up and then down again. That's the methane that we could capture and generate electricity from. Methane is about 8 times more potent of a greenhouse gas as carbon dioxide. So with landfills, methane is the primary greenhouse gas concern. I mentioned in the groundwater contamination lecture that phytoremediation, planting trees in landfill caps, these older landfills that don't have methane recovery, is one way of reducing the amount of methane leaving the landfill. I was going to do some PhD research on that if I went to a different university for my PhD. And then you can see leachate, the COD and BOD, large amounts that can come out in the leachate, but other things like acids that can drain out, as well as organic nitrogen. Composition, so this is a similar thing. How much BOD? You can see BOD 5 young leachate 10,000 milligrams per liter. Huge amounts. You know, on the order of 10 to 100 times what a municipal, what raw sewage would have coming in. So very potent waste. That's why these protection systems have to be so advanced. So this is all municipal solid waste we've been talking about. There's another category of waste called hazardous waste. And these are any wastes that are considered either toxic or potentially toxic, flammable, corrosive, or explosive. Radioactive waste is even in a separate category that's not considered hazardous waste, but radioactive waste. So hazardous waste has a whole nother set of regulations that applies to it. These cannot go into a normal landfill, but need to have a hazardous waste facility, hazardous waste landfill usually to dispose of them. They can be extremely expensive to dispose of safely and properly. And so we're not going to talk a lot about that, but that's distinct from municipal solid waste, and all the regulations associated with those are distinct. And finally, as I mentioned, there's a few videos that I've posted on Foxtail that I want you to watch as part of this lecture. There's 4 of them. I think combined they're about 20 minutes long. And so watch those 4 videos. There's a landfill video, a waste to energy video, and then 2 videos regarding recycling and, well, one about recycling and composting, and then another about the current state of recycling. So watch those videos and then take the quiz.